me start. So I basically give you a grand tour of the graph neural network in the last lecture. Is by all means very superficial, but then the idea it's kind of like you go to Olive Garden and you actually order the tour of Italy. You probably won't taste all the best food in Italy, but you get a general sense of what American Italy's cuisine look like. So here I want to move to the manifold, and then next lecture we would have the presentations, and after that I want to complete the whole circle to talk about some relationships or some work that use both graph and manifold in an interchangeable manner to actually help us learn the topology and the geometry of the data and using it for engineering practice, in particular for engineering mechanics, okay? So here we go back to the manifold. Again, we deal with the same problem in the sense that the majority of time we have a point cloud, and then that point cloud can be, that individual data point can be related in a discrete manner that allow us to form a graph, or they can be continuous. In many cases, you assume there's some smooth relationships, okay? For example, I want to predict whether the height of an individual person is related to the income, that the height is actually a very continuous variable. So it makes sense to model it as a continuous field, a continuous variable, and then the income could be another one. Then you can actually using it to form a manifold. Okay. Now here, in lecture 10, which is the field lecture, before I give a very superficial introductions on the manifold, and I think that this time I would actually try to give a slightly less superficial introductions of the manifold with more details. And then if you choose to use the manifold as your final project, hopefully that would be helpful. I will probably going through more slowly, and then feel free to ask me any questions. Okay, so I just want to show this, and then for people working on topology, they're the same thing. We talked about that before. And basically that is because we can actually apply a continuous mapping, basically just a deformation mapping to map it from one to the other, and that mapping could be one to one. Okay, meaning that you can go through it from here to here, have multiple deformation gradient if you are into that continuum mechanics thing, or you can actually go through the opposite route and you can actually have a continuous mapping. Okay, so in terms of topology, this gives us a very interesting characteristic in the sense that even though they look geometrically very different, topologically, we actually could say that they are actually quite equivalent. But why do we actually care? This is actually the questions. And here I would actually talk a little bit more about those details, okay? And then I'm going to explain the concept one more time, but this time with a slightly more focus on the surface in 2 dimensions, and then generalizing it to a hypersurface. Okay, so we talk about why we study the manifold before. In general, a lot of time we can assuming that the data point that you get are part of the manifold. Okay, like what I'm talking about the previous example, the height versus the income. We can, if you consider the height as one basis and the income as another basis, it form a space, in particular Euclidean space, and you can actually assuming that that relationship is actually on some manifold. Okay, so you can think about it as a functions, but you can also think about that it's actually a subset of the Euclidean space. Okay, now if you consider it as a subset of the Euclidean space, then there are a few things that we can do. The first thing that we can do is that in the data set, is there any way I can actually find a low dimensional structure? Okay, like what we explained in all the other applications, we usually in a lot of machine learning tasks we deal with very high dimensional data, which is actually quite different than mechanics. When you write the yield surface, you may deal with 2 invariants, 3 invariants. But in other applications in machine learning, like drug delivery, you may consider 89 or 120 Euclidean space that are much larger. So in this case, then the incidence of the point, if you have a couple thousand of points to actually curve fit Euclidean space that are actually in dimension 2, you can probably have a lot of points and you can curve fitting it. And if you have very high dimensions, that number of points is actually very, very small. So you can actually curve fitting it. You can matching all those points in many, many different manners. Okay, so the dimensionality is a problem. But here it comes is that if we can find a low dimensional structure, then maybe I can actually analyzing it in the low dimensional structure, and all those high dimensional issues can be somehow cured or at least under control. Okay, so we can somehow finding it. Then the question is how to do it. Okay, so in order to do that, you need to do two things. One is that you need to actually have the high dimensional manifold, not the data point. Okay, the data point live in the manifold, but it's not the manifold. You know the difference between the two. So you have discrete observations of those data, but you don't know what is the ground truth manifold. So the first task you need to do, you need to ask a lot of time, is what is the manifold that the data is on. Assuming that you're making a hypothesis that those data are the manifold. Okay, so this is step one. Step two is think about whether I can find a low dimensional structure. Okay, so when people say that I'm doing manifold learning, it actually means very different thing. It can mean one of them or both of them. Okay, so the learning the manifold and then deducting the low dimensional structure to it are actually two different problems, but then you need to have one in order to do two, or sometimes you can directly have the point cloud and try to learn the low dimensional structure. Okay, we're going to talk about both of them, and then we talk about it before, and then I just want to show you some of the manifold. In general, you can think about manifold in a three-dimensional space as simply a description of the object. Okay, and notice that all shape or topology. Notice that in all of these shapes that are actually in 3D, okay, locally you actually do have a tangential space that are only two dimensions, right? Okay, for a given point, I can actually have a tangential space, and each of the point will give you a slightly different tangential space, and then the problem is that at a different point, the tangential space is different. Okay, if the tangential is the same, you probably don't need to introduce a manifold, just do it in Euclidean space, everything is flat, right? And that if you want to solve problem or formulate problem there, dealing with the manifold and dealing with the Euclidean space is actually need to take account of that difference. Okay, a classical problem is shell or cable or actually beam. If you consider the geometrical nonlinearity, they are actually manifold. Okay, you see what I mean? So for this problem, the one clear characteristic is that in those systems, you don't really have a global coordinate system. Okay, locally for each tangential space, for the point, it also doesn't have a. Yes.
So I'm looking at those non-manifolds to the right, and they look very non-differentiable. Is the absolute value function an example of a one-dimensional thing?
Yeah, I would actually talk about the precise definitions. Okay. So I will actually talk about that. Yeah, so those are actually the reason, but I will actually listing them in a more rigorous manner. The last time I just give the overview. Okay, but this is actually good observations. Okay. Okay, so this is actually basically one iterations, and you can see it in also machine learning literature, is that they try to solve a heat conduction problem on a manifold, okay, or for Earth, okay, if there's a heat source or there's a webbed mesh, and then you say there's a heat source, and then you're propagating it. One actually interesting thing is that if you're actually solving it in the Euclidean space, you just need a Laplacian operator, right? Okay, on the manifold, you need a generalized version of the Laplacian operator. The Laplacian operator won't work Okay, because you're actually dealing with this surface that actually propagating the heat in the tangential directions. Okay, you see what I mean? So there are machinery that need to be generalized, and then the sense of distance and length are actually distinctive. Okay, in the vector space, you can say length and you can say norm, and you can say the distance, and all three ideas are actually very close to each other or actually identical. In the manifold in general, that's not to do with this thing. Why are they actually case? Something to the matter. So let me go through that. Okay, so this is actually the Rand's diagram. Okay, so actually the interesting thing in mechanics is that we study this first. A lot of you in vector calculus will know what is the inner products. Okay, so inner products give you the sense of what? If I have a vector and then I actually compute the inner product, so what does it give it to you? It gives, yes?
Oh, nothing, you can continue, sorry. Huh?
Oh yeah, you just, okay. So the inner products is actually one thing that actually very important for you to, you can using it as the raw measure to measure the length angle and actually check whether it is orthogonal. So V dot W, okay, what's going on? Okay, or you can actually using the inner product to check, to actually define the length angle and orthogonal, of the idea of being orthogonal easily. Then it go to the norms. Okay, so norm basically just a vector space equipped with norm that are actually well defined. And then the norm is actually very important in the sense that it gives you the sense of length. Okay, like what we talked about before, if you go to Manhattan and then you only have 1 second to guess how much the tax dollar, how many money you need to pay to actually hire a taxi driver to go from point A to point B. You may, if you only have 1 second, you may want to use the Manhattan norm because the Manhattan really is a grid system that actually go like this. Versus if you actually want to measure 2 points on a flat surface on a desk, you may want to use a ruler and then you get an equivalent norm. L2 norm, right? So the norm gives you different sense of length. Okay, in the case of the Manhattan case, this would be the length, but not this one. Okay, in the measuring 2 point, in a very generic manner using a ruler, then you're actually measuring the L2 norm, and that norm is actually, that norm space is actually a generalization of the inner product space, which means that you can have a norm that are actually not induced by inner product. And then there's a matrix space. So matrix give you the sense of the distance, and they could be sometime very close to the norm. But here, the manifold is actually in here. Okay, so the manifold are actually connecting these two. Okay, in a very interesting manner. Globally, you just have a topological space. You have some sense of closeness between the point. You don't actually indulge any measurement that allow you to measure it globally. Okay, you haven't defined it yet, but locally, in a tangential space, you do actually have the tools to measure the distance and the length and the angle and everything, but only locally. Okay, so there's a two view on that in order to understand the manifold properly, and depends on different type of manifold. It has a different generalizations. What we talk about connecting this to this would be a Riemannian manifold. A Riemannian manifold require that the tangential space are actually inner product space, versus in the thin-cylinder geometry, you actually relax that assumptions. Here, I won't talk about even more general abstract manifold. I actually don't understand all of them, so I would actually go for the easiest to understand, more that actually only require you to generalize your understanding on the Euclidean space. Okay, if you don't understand what is Euclidean space, I also give an overview, but it's basically a very close to vector space in the sense of Gilbert string. Okay, also helpful. Okay, so here I just need to talk about what is topological space. I think And then we talked about that before. And then this is a very abstract thing. In order to define as a topological space, you need a set. Okay, so that set could be anything. It doesn't even necessary to be a vector space or anything, but it also need to have a topology. Okay, so this is a little bit abstract. So let me say it. Let me give some example later. And then it has these 3 criteria. Okay, so the set itself and the empty set has to belong to that topology as well. Okay, and then any subset of that X, any interactions of that has to also be in this topology, and any union of it has also to in a topology. Okay, so example is a circle is a 1D topological space embedded in the Euclidean space. And that, so let me give some example here, and then we can check it one by one. Okay, let's say I have this family of set. Okay, so A, B, C, D, they are actually all set. Okay, and then together I have a collections of set, which is actually X. Okay, is that understandable? Oh, sorry, more accurately. Let me say it again. Sorry, I think I'm making a mistake. Let's say I have a set X. Okay, and then this set have 4 elements, A, B, C, D. Okay, if you think about money, you can think about it as Japanese currency, US dollar, or I don't know why I always think about money, but you can think about this thing as 4 different things, or actually animal, chicken, number of chicken in a farm, number of duck in a farm, okay, whatever, just for entity, okay. Now, in order to fulfill that, let's try to build some topologies actually to see. So topology is actually basically a family of those sets that satisfy all these 3 rules. Okay, so I will put O as an empty set. Okay, so I actually don't know how to draw these things, so I just put O there. So O here means empty. It doesn't mean you have an element 0, okay? That's a very important. So empty set is a set that have no element. And then a set with 0 is a set with 1 element, which is 0, and they are not identical. Okay, now I have an empty set, and then this A, B, C, D. So let's check whether it hit the requirement. Okay, is that okay? Do you understand what I'm trying to do? I'm just trying to give example to check whether T is a topology. Okay, so I have a collections of subset already, which is actually A, B, C, D. So now topology candidate is actually this family of set. I have 0 and A, B, C, D. So just 2 subset, okay, in that family. And obviously I have the empty set here. And then I have the X itself in the set, right? Okay, does that make sense? Okay, so criteria 1 is actually fulfilled, right? Can you all see that? Okay, now let's move on to the intercept problem. Okay, is the intercept of them actually, what is the intercept of them?
Are you defining that as collections of ordered pairs that you're defining?
It's not order. Yeah, here the family of it has no order. It's not an order. It's not a multi-set. It's just a set.
What are you defining by interaction then?
Interaction is actually basically the element that are both in the 2 set. So here I have 2 sets, empty and ABCD, right? So the interaction of them is.
Should it be intersection?
No, I have 2 sets, empty and ABCD. And what is the intercept of them? What is the set that in both sets? Nothing, right? Okay, I have nothing. What is the nothing intersect with anything? Nothing, right? Okay, so now then, is this on the top still in the topology? It's still in the topology, right? Because the topology are actually meet the empty set and ABCD, right? So criteria 2 is okay. Now what is the union?
It's a set that contains either or.
Yeah, that would be or, right? Union. You basically union, put the entire set, combine it together to find as many elements as possible. So the union of nothing and ABCD would be simply A, B, C, D, right? Okay, nothing. Okay, so if this is actually all true, and in fact, it's a particular name for it. It's actually called trivial topology. Okay, why is it called trivial? Of course, you have a set and you have the empty set. These all three criteria always fulfill, right? So it's actually called trivial topology. Okay, yes?
I think by belong, you're saying that everything's a subset, right? It doesn't have to be a member, but it has to be a subset, if there's that distinction too, right?
So where is the word belong?
1 and implicitly in 3, and that just means that's a subset.
Yeah, it's an element, right? Belong means that it's an element in that set.
Is it subset or element? Because I remember asking Stack Exchange about this. I think.
So element is an individual element, and then you have two elements, you can form a subset. The two or more elements, you can form a subset. Even one element would also be a subset of that thing, right? So like what I'm saying, okay. So let's say I have 4 elements. Let's use a chicken, elephant, tiger, and cat. Okay. So there's 4 elements in that set, right? Okay. So I can also say that the cat and tiger itself form a subset, or I can say that cat itself is actually both an element and a subset, and the tiger is both an element and subset, right? Because I can just pick one and form a subset.
Okay, well, what about like, okay, so at the top you have like let x equals a, b, c, d, right?
Mm-hmm.
You can't say that x is an element of itself. You can say that x is a subset of itself, but it can't qualify as an element of itself.
You can have a one set that have only one element. You see what I mean? You can have a set that only have one element.
Yeah.
So.
Okay.
Yeah. Okay. I think we can talk about that later, because otherwise, if we go through also the linguistic then and topology, that would take a long time. But I think you basically get the general idea, and then we can go through it. So let me go through the second example. Okay. So I have that topology, and that it includes 4 family of set. Okay, these 4. Okay. So is the first one okay? First one is always in this sense is okay because I have this and this, right? Okay, so I fulfill the one, and then how about the second one? Interactions. What is the interactions? Okay, so this is actually the important part. It's not any, is you have to actually randomly pick any 2 interactions and it still fulfill that condition too. Okay, so what is the problem here is that if I actually look at the intersections of A, B, and B, C, what is the intersections? The intersection would generate another set that are B, right? Okay, but B is not in that 4 setting, okay? You only have C, A, B, B, C, and X, which is actually contain A, B, C, D, but you don't have actually a set that only contain B, right? So this is actually game over for 2, and you can also check the condition 3 is also not meeting it, because if I do the union, any union with the trivial with the empty set would be okay, right? Okay, because the union of an empty set and the original set is just the original set, right? But here, I would not fulfill this criteria because ABC is actually not inside that family of topology. It's not one of the collections, okay? Does that make sense? Okay. So you can actually check this criteria, and then you can also check the last one. Do you want to go through that last one, or you get the idea? Okay, did I? Okay, so you get the idea? Okay, so why do I actually care about that? We don't care about ABC, right? Okay, but usually ABC, they are actually some kind of subdomain in the topology. That's why we actually care. Okay, so the subdomain, yes?
Oh, sorry. So you basically can't have 2 touching compact sets if you're dealing with like continuum or continua, right?
Sorry, can you say it again?
Yeah. So if like A, B, and BC like intersect, right?
Mm-hmm.
So if you have 2 compact sets that are touching, that is sets that contain their boundaries or endpoints, then you have to have that like boundary point explicitly like by itself, right?
I don't have an answer right now,
Yeah.
but if you send me email, I can think about it. I think that I don't know, so that will be the honest answer. Yeah, I need to think more carefully. Okay, but you guys get the general idea. But I think that okay. So anyway, I think I make some change here. But here you can actually seeing that a circle would actually fill that criteria. And then another thing that could fulfill that criteria is actually like the torus. And there are many other shapes that actually fill that criteria. And also there's a machine learning paper that actually indicate that some of the so-called manifold learning are actually building the manifold that not fulfilling those criteria. So if you actually want to really construct a manifold, which a lot of time could be alternative to build a functions, and then you actually need to check whether what kind of manifold you're trying to build and whether you actually first fulfill the topological space criteria. Okay, so let me give some example. Okay, so example on this, explain a little bit. Now, let me go through that again with that circle. So the first thing that related to the machine learning is a norm. Okay, so and then a lot of time we don't really build the machine learning in the manifold or in a, but you probably would actually measure it in a norm space, and you can probably already knowing that if you put a different norm, you get a different result, right? Okay, if the result is perfect, then loss function go to 0, and then all of them collapse into a point, which is actually not a problem, okay? So all of them in the topological sense are all spherical, or actually a ball, okay? Unit ball in particular, but they are different kind of unit ball. Okay, and then the reason that they get different geometrical shape is simply because you have a different norm. Okay, so the norm indulged to it is actually affecting your judgment in the supervised learning. Let's say that this is actually predicting the stress, volumetric and derivative stress. And then you use the L2 norm, you are actually trying to shrink the distance, the earlier. You would actually basically saying that I would actually measure the difference between this and then the measure, then the difference between that volumetric and derivative stress, and I'm trying to shrink the circle as much as possible. Okay, that's the geometrical intuitions. If you do the L1 norm, that means that you use the Manhattan distance, so that means that you try to make sure that if you add two Euler together, how to be minimizing it, and then you get this shape. If you use the L infinite norm, that means you only care about the maximum Euler term, then you actually get that. Square. Okay. So when you do the machine learning, this is also another thing. You can actually eventually you get the tangential space, and you can use the inner product, or you can use the norm as well as that can be used as your loss functions. But which one makes sense? Okay. So which one do you think it makes sense? They're all equivalent norm, okay? Meaning that if you go to 0, one go to 0, all of them go to 0, right? That's for sure. But then the problem is that they lead to different landscape, okay? So what landscape is actually implies how difficult you solve the optimization problem, okay? You see what I mean? You can try to cook up some functions and see how does the L2 norm actually evolve. Function 1 and function 2, and then you have an error, right? Okay, so you can actually using it to check the landscape of the response, and that could be also be if you really don't want to do anything difficult, that could also be a cost project just to see what happens if you use a gradient-based optimizations. And one of the actually important thing that we often forget is that these norms are actually used to define a derivative also. So if you use a lot of time, we don't see that because we just use the L2 norm. So you don't really see that. But if you think about it in a very strict manner, you can actually pick out a norm to actually measure the derivative, to create a derivative, or the measure of distance. Okay. So now the first thing that we talk about is the Griffin's Euclidean space. We talked about it before. Basically, it's a finite dimensional space. Here we restrict it. in the finite dimensional state that also have inner products, and then the square root if you use the L2 norm, then the norm is simply the actually let me use a more accurate language. It's actually the length of the vector, but it's also a distance of the vector. Okay, that's because everything is actually flat here. And then the consequence of actually having the same distance and length is that you actually have a global coordinate system. Okay, so if you formulate a U surface using the stress, then the stress would be the avian space that actually could be the global coordinate for the U surface, for example. Okay, but if you actually want to model the U surface as a manifold, then then you actually need to, then the local coordinates on the manifold would be actually different than the global one, and it will be one dimensional less, right? Does that make sense? Let's say I have a surface. Surface is actually locally only 2D, right? Okay, but they are actually, the tangential space actually would have different basis vector. Okay, we talked about that before. This is actually exactly what I'm talking about. You can actually using a different norm and then to measure the difference. So if you use a different norm, you may actually get a different sense of what is actually difference, and then you may actually from that get a different Jacobian. I think that part you all know what it is, right? So the geometrical intuition is the following. Let's say I actually have, let's do it in 1D. I actually have a functions that are actually x, and then I actually have this, okay? You see what I mean? And then I actually evaluate FA here, okay? And then I evaluate FA plus H here. And then what I actually want to, should fulfill is that if I actually have a very linearized distance measure here, all three things combined, if h become infinitely small, h is actually the distance here, then this whole thing becomes 0. Okay, does that understandable? So it means that I can have a very complex pattern globally, but if I actually keep reducing the distance of it, if the perturbation becomes smaller and smaller, eventually all three terms are actually identical, which means that locally, if you actually perturb it small enough, then the whole thing is just linear. Okay, you get the understanding. The whole thing is very nonlinear, but if I actually keep reducing the space, eventually I will get something that is just a straight line. Okay, and then the difference of it, that linearization's versions of the difference, if you put it together, give you the Jacobian matrix. Okay, so the Jacobian matrix basically in a higher dimensional case is actually tell you at a given point where to go in different directions to actually perform in a linear manner, but capture some the gradient of the structure. Okay. Okay, I think you probably already all know. So. Okay, so and then the partial derivative is actually the very similar idea. I actually would have a point and then I perturb it in only one direction instead of the Jacobian. I try all the different orthogonal directions, and then I can get a local term. The partial derivative is actually just a scalar to measure the difference. The two are actually, and then I can also do it in a directional term, almost identical. The only difference is actually the perturbation is now a vector. Okay, so this part you all understand, and you probably know it from your AP class or your undergraduate calculus. Now we move to surface. So what I plan to do is that we introduce the vector. Now we introduce the regular surface, and then the regular surface is actually a special case of a hypersurface, and then the hypersurface is a special case of a manifold. Okay, so and surface is actually pretty easy to understand because I think that you all see surface before, right? Anyone haven't seen the surface? It would be yes.
Do Jacobians have a spectrum of eigenvalues as well?
Yeah, Jacobian usually of course it has eigenvalues. So eigenvalue actually tell you if you actually look at the maximum. If you actually look at the right directions, you can actually get rid of all the shear term and then see what is the deform. So a circle can always you can always describe the circle into ellipsoidal using a second order tensor. But if you're actually looking at the principal directions of the change from the circle to the ellipsoidal, this would be the length change would be the eigenvalues of the stretch. Okay, you see what I mean? So let me give you an example. If you have this shape, and then I perform a pure shear, I will get this shape, right? Okay, so it apparently I break the symmetry because I apply pure shear, right? Okay, but in the principal direction, I would look at things in this perspective. And then what I have is just making it a little bit longer. So it looks like I did not break the symmetry. The reason is actually related to the rotations from the original coordinate system to the principal directions. If I'm moving it to the principal directions, I would take out all the shear component and it looks like it's just a tensile and compaction direction in the principal directions. Okay, in fact, there's lots of people studying the topology are using that kind of analog to help them understand how does things deform. And that mechanical intuitions is actually very uniquely important to understand differential geometry, which I won't say that I understand it. I just try to learn the minimum for the machine learning tasks that we have on hand. So yes, okay. So this is actually the intuitions. So do you guys get what I'm saying? Okay, so let's say I have a deformation gradient, or actually more accurately, let's say I have a small string. I can always get the principal directions, but if you think about it, what I'm actually doing is simply rotating this configuration into here and then just take out all the shear and then apply the compaction and tensile in that directions. That would be equivalent to applying a shear. Okay, so the first important concept is actually the local parameterizations that are actually different. You may notice that if you actually define a surface in a level set, you don't need that local parameterizations because you already have all the point cloud in the XYZ directions. But here, what I actually instead want to do is to create a local parameterization that only work in small regions, okay, within a neighborhood and a point, okay, or maybe within a patch. So this is actually the definitions. I should give this is actually coming from Frederick Fong's book in Hong Kong UST, and I actually put that reference into the course web page. If you want to look at it, it has a very good introductions that are very intuitive and actually start with a surface locally in the Euclidean space of 2. So that actually help build the intuitions. So what is a local parameterization? The local parameterization is actually one local coordinate chart that only work on a subset. Okay, your global geometry can have many of these subsets, but I'm looking at one local subset right now, and I actually want to build a parameterization so that I can actually fulfill the following criteria. I want to make sure that if I map it from my parametric domain, and then I actually map it back into the open set of the Euclidean space. I would if this is 3D, then if this is actually mapping into 3D, then the codomain is also 3D. So I don't have any reductions on the dimensions. Okay, so this is actually easy to understand. Another concept that are actually important is that the mapping between the local parameterizations to the global to the shape itself, it has to be a 1-to-1. Basically, the inverse of it has to exist. Okay, does that make sense? So I can, for example, I have R cosine, and then R sine, actually that probably describe the circle, and then I should be able to actually describe it. I should able to map it back and forward without losing any information. So it's a bijective, meaning that it's actually basically 1-to-1. Okay, so that part is also easy to understand. Okay, then the next criteria is that the cross product cannot be going to 0. Okay, so why is that? Okay, so this is actually it's actually easy to understand when I draw the figure. Okay, so when I actually mapping this onto these directions, I'm actually taking a derivative of these two directions, and then the cross product is actually the normal directions. So what I'm basically saying is that they cannot be parallel to each other. If they're parallel to each other, you lost the dimensions, and then it collapsed from a 2D surface into a line, and etc. So that won't fail, because you actually need to able to map between the 3D description on the surface and then the 2D descriptions. So, and one last thing that actually to represent something a smooth surface, which we actually sometimes will require, or we will assume to have that property, is that we're just assuming that this is C infinite. So meaning that I can take as many derivatives I want and I won't get a jump. Okay, so this is actually and if this is successful, then I actually obtain a local coordinate that I actually only work for that are actually working for a subset of the Euclidean space. Okay, so in 2D, so this would be the Euclidean space. I have x and y, so this would be something like this. So this would be considered a subset. In a 3D case, x, y, and z, I can actually have a surface, and then the surface would be obviously a subset of the Euclidean space. And then for that, I would obtain local parameterizations. Yes?
So, I mean, obviously, if we're like in functional analysis land, if we're dealing with like norm spaces, you get a very generalized notion of a norm. Like it only has to obey a few rules, can be a lot of things. You get a very generalized notion of a dot product.
Mm-hmm.
Is this a very generalized notion of a cross product? Or
No,
is it
it's just a
exactly-
classical dot product
It's
in
like
the.
what you would see in like calculus 3, just like crossing two vectors, cross product, basically.
I won't necessarily think that is a generalization of the cross product. So far here, this is actually just on the. I would say that it's probably the classical definition of the dot product, of the cross product, but not any generalizations of it. So your cross product, your understanding of cross product apply. So you have two magnitude, and then you get the new thing in the orthogonal directions. Okay. And then okay, so far so good. Here that we mentioned here, meaning that it doesn't degenerate, and then the homomorphism, which one? So a lot of this is actually for
Sorry,
commit.
did you say?
Let me go this.
Sorry, did you say the derivative needs to be 1-to-1?
Yes.
Well, I know that if you're dealing with isomorphisms in algebra or in actually graph.
Now, for example, this is actually important. So this would be a 4 coalition chart to cover the circle. So you can consider that 4 local coalition chart combined will give you a circle. However, I can also write this. Or actually, maybe I should swap the order. I'll cosine and sine. Okay, and then I can actually define this as anywhere from 2 pi and 0. But in this case, I would actually able to cover everywhere, but not at the top. Okay, because I actually did not include, and also not the top and then the south pole, because that one is not equal. But here, the way I actually described it, because of the overlap thing, if you separate it into multiple coordinate chart, then you actually can create a topological space that cover the entire, that actually have 4 local parameterization that cover the whole thing. Okay, so this is actually a well-known issues on the using the polar coordinate. I don't know whether you know the North Pole and South Pole are not well defined. You can approaching that point, but because it's an open set, you don't include the 0 and 2 pi. Okay, but if you actually cut it into 2 pieces, or actually at least cut it into 2 pieces, maybe something like this, you can actually cover the whole. These 3 criteria, and then it's actually meaning derivative to be 1 to 1. Okay, so then we talk about the concept of, here I just want to talk about one thing that are very important. So do you guys know what is an open set and what is a closed set?
Yeah.
Okay, so open set is the thing that doesn't include the boundary. Okay, so actually for elasticity, for parasiticity people, that is actually very easy to memorize. If you actually consider the elastic regions, I have an open set. If I consider the admissible range of the entire thing, including the yielding, then I have a closed set, right? So the open set is actually important also for the concept of neighborhood, okay? Because a lot of time we are actually looking at the tangential space of something, and then if you actually have a closed set, then you're at the boundary that you can only have you can only preserve it in one direction. Okay, so here we would actually consider a regular surface as a subset of the Euclidean space R3. Okay, this is because you consider surface, not a hypersurface. Okay, physically a surface is always a subset of the Euclidean space of dimension 3. That part makes sense, right? Okay, everybody get it? Okay. And then where K is simply anything union n and the natural number. So natural number is just any number you can use for counting, okay, not include negative. So 0 all the way, and then the union with infinite, because you can have a C infinite surface. So that actually separate. So we actually write something separate for the infinite. So, and in R3, at every point that actually belong to that, there exists an open subset U that actually belongs to R2. Okay, now this is another concept. So now U is actually here, okay? So the original M is actually here. So M is actually a subset of the Euclidean space of 3, and then the open subset U is actually here, that a subset of Euclidean space of dimension 2, okay? Now, if I actually can, for every point of it, for every point in here, if I can actually define local parameterizations that help me create a local parameterizations from here to here and vice versa, because it actually have to be bijective. Okay, so if I can define a mapping that map here to here and then reverse here to here, then fulfill that, not just the mapping between this flat surface onto this curved surface are 1 to 1, but the derivative is also 1 to 1. Then we actually could we would call it a regular surface if it's actually C infinite surface, basically a smooth surface. Okay, does that make sense? Okay. By the way, why do I actually also need the tangent to be 1 to 1? But why do I actually also need
preserve the full structure of the graph? And one of the important parts of an isomorphism is that the operator itself needs to be linear. So
yeah,
f on
so
A plus B is equal to f on A plus f on B, basically. And since derivatives are a generalization of a linear operator, I think they'd have to satisfy that. I don't know if that's the answer.
So if you actually have a tangential space, later on we will talk about that. If both of them have a tangential space and then they can also have a 1 to 1 mapping, you can actually have a more you can actually construct transformations of the coordinate system, because one of the important things later on we will talk about is that the coordinate system doesn't exist even in the subspace or even in a patch, but only exists in the tangential space. Okay, you see what I mean? So this is actually the whole domain. I cut it into two. Okay, and then there's an overlap, there's a transition mapping. However, this whole thing still doesn't, even I look at just the red zone, I don't have a coordinate system, but the tangent of it has a coordinate system. Okay, so if I actually, okay, so I just want to show some example where parameterization is not possible and you won't necessarily consider it as a regular surface. This is actually one possibility. And this is actually another problem that I think this is called Kind-Sabato or something like that. This pink is actually lead to the violations of that definition of the regular surface. Okay, so now this thing is also related to the level surface. A level surface is simply a level set for given values. You also get a surface, right? You see what I mean? I have a three-dimensional scalar functions that are actually level set. If I actually say that I want to write f equal to 1, I would also get a surface. Do you understand what I'm saying? Okay, so for example, let's say that, let's consider in 2D. I have a level set that looks like this. Okay, I can say that I actually locally get a curve in R2, right? Because if I only look at this, if I actually only look at the, if I actually only look at here, look at the blue curve. Okay, the blue curve is simply like this. Okay, so and locally you only need a R1, right? Can you see that locally you only need R1? Because it's actually locally only 1D. Okay, you see what I mean? If I so in this dimension, so it kind of help you to understand it, when you actually want to create a manifold from a 3D ambient space, then you actually have a surface. If you want to create a manifold that are actually from R2, then you basically get a curve, right? And then in this case, then the surface thing will be degraded into a curve. In that sense, locally, I only need one-dimensional coordinate system. Can you see that? Versus in 3D, if I actually want to define the surface, I would actually lose one dimensions. Locally, I have a 2D coordinate system. Okay, so and then that actually have one more criteria is that for this particular case, I can actually define a level set functions that are actually smooth, and this is actually exactly implicit functions. If you deal with phase field, okay, phase field factor, what is phase field factor? Phase field factor is actually levels functions to help you represent the actual manifold without dealing with the manifold. Does that make sense? Okay, so if you actually create a manifold, or actually maybe not necessarily a manifold, but actually a surface. Okay. If I basically map it into values, and then what I actually need is that in order to be a rectangular, in order to be the regular surface, I need to check whether the gradient of that scalar functions is actually not equal to 0 at all point, or at all point where the inverse exists. Okay, if this is actually the case, then we also have a regular surface. So this is actually quite abstract, but let's look at this example. So x squared plus y squared plus z squared equal to 1. I think everybody understand what it is, right? Okay, basically just a ball, just a spherical in R3. Okay, so it's actually a level surface for the G-1, where you basically have these functions. Now, if I compute the gradient of this, then of course, if I simply put this function there, right? And then I take the derivative, I get 2x, 2y, 2z, right? Okay, does that make sense? So x squared plus y squared plus z squared is actually gx, y, z. Okay, and then I take the gradient g. So of course, I will get a 2x in the x direction, 2y in the y direction, 2z in the two directions. And obviously, at the origins, okay, at the origins, then the whole thing becomes 0, right? Okay, so that's a problem here. Because I need everything is not equal to 0, but this is not equal to 0. But here is actually what is the interesting thing about that. The origin is actually not in a global unit. Remember, the North Pole and the South Pole are not included into the parameterizations. Okay, you see what I mean? So you actually 0 is an open set, so the 0 is a limit, is a boundary, but you actually never have 0 as one of the admissible element. Okay, so even though this is actually this look like is violating that, but because the origins is actually excluded, then the whole unit surface is actually a rectangular surface. Okay, so you can think about another problem, and then you can actually check. It's actually not. Now, another concept that are actually very important is in between two subsets of the surface. Okay. Now, in the manifold, remember you no longer have a global parameterizations or global coordinate, but you have the local one. Now, let's say that I actually have a representations that are actually going through from here to here, and then both of them belong to a different local parameterizations. Okay. Now, there is a transition zone here. Okay, what do we want for this transition zone? Okay, you can kind of imagine. So we actually want to, because both of them, let me look at this figure. So both of them would actually have a different local parameterizations. So you basically have different U and V. So you have different parameterization track here to actually help you mapping into the structure, and they have an overlap zone, right? So the part that are actually excluded from the intersection, you don't really need to worry about another local parameterization. So meaning that for this part, and for this part, you don't really need to worry about what is the other parameterization, right? Does that make sense? Now here, what you actually need to make the whole thing consistent is the following. In this transition zone, can I actually complete the looping? Can I do a loop and then loop it back into from one local coordinate system to the other coordinate system? If I can loop through it, then actually the two local coordinate systems are consistent with each other. Does that make sense? Now remember, for each of them, they are actually bijective. So the f minus 1b exists, and then the f8 alpha minus 1 exists, right? So if the whole thing is actually correct, then what I actually need to do is that if I start here, I map it into the manifold, and then I have the inverse of the FB, map it back to here, and then I should be able to actually construct a mapping that I actually complete the loop, and then they should be equivalent. Okay, this is actually what the transition map is about. Okay, now if you're actually able to complete the loop going from one parameterization to the other parameterization, you are actually changing the coordinate system locally. Does that make sense? So you have two in the overlap zone. You have simultaneously have two local coordinate systems that you can think about which one to use, but given the condition that the transition map actually need to be well defined, and the criteria is that you actually need to able to have a change of the transition without deforming the M. Okay, does that make sense? Okay. Does that make sense? So this is actually, and f minus 1 always exists. This is actually a requirement to be bijective. From here to here, okay, I can actually take the derivative. The important thing is actually to consider this graph. So why is it related to machine learning? Why is it related to machine learning? This is actually from mathematics, but why is it related to machine learning? The answer is actually very simple. Because a lot of time we don't know what is that mapping is, okay? We don't know how things should deform. How do I actually find the coordinate? How do I perform those mapping? And in order to find those mapping, you can do it in a supervised learning manner or do an unsupervised learning manner. Okay, one classical example is to create a surface mesh. Okay, what is a mesh? It's a discrete versions of the manifold. And then basically you have a geometrical shape and you actually want to make a graph out of it. But before that, you actually need to understand what is a manifold, and you can actually doing it in a coordinate chart. Okay, so does that make sense? Okay, so but in this case, actually, I think the notation is really nice. It's actually using the O, and you see all of them are actually dot. They are not close. Okay, then you don't. Okay, now this is actually also another important ingredient that are actually kind of intuitive. So in topology, there's a very distinguished work between line is straight, curve that are not necessarily straight, but curve can include line, okay? And then plane and surface. Plane is actually flat and surface is not necessary, okay? That is also important. So surface, the set of the surface including the flat plane, but then the plane itself is a special case of the surface that actually have one local ingredient. Now, you can actually always create a flat surface by actually consider a given point, okay? And then from that given point, I actually can create Euclidean basis by taking the derivative of that parameterizations, okay? That parameterization, that of it with respect to the local parametric space, and then for the two orthogonal bases, I can actually create a vector. Now, these two vectors are not necessarily orthogonal to each other, but they need to be independent to each other. Okay, you see what I mean? So the cross product need to be non-zero, but they don't need to be 90 degree. U and V need to be 90 degree. Okay, you see what I mean? Does that make sense? Okay, you start from here, but you may map it. After you map it, it becomes something like this. But this is still okay because I still have the orthogonal component that allow me to span the R2, right? Okay, if I actually start like this, 90 degree, and then I map all the way, and then this line somehow collapse into this, then this is not okay, okay? Because I actually degenerate the dimension, actually reduce the dimension too much. Now here, I can actually, the tangentials, the tangential plane are actually defined simply as the space that's spanned by this actually derivative term. Okay, does that make sense? Basically, I actually create a basis here, and then from using that two bases, I can form a Euclidean space. Okay, does that make sense? Okay, so now there's a very important concept here. If I pick a different point, I would actually get a different tangent plane. Okay, you see what I mean? Versus if I actually already in the Euclidean space, what happened? So the Euclidean space is actually of R2 is a special case of a tangential plane in R3 in which I pick all the points everywhere I get the same tangent, right? Okay, so this is basically the idea of being linear. Does that make sense? Okay, but here for different point I get a different tangent. Okay. Now this is actually interesting. If you actually have 2 points that are very close, I probably can just use the tangential space to measure the distance, right? It doesn't hurt that much. But if I actually have a point there, you can actually kind of see that. If I want to measure the distance between this point and this point, okay, if I actually look at the tangential space, I will have multiple straight lines, right? If I ignore the geometry, I will actually just linking them with some Euclidean space, with some norm, maybe a Manhattan norm or maybe L2 norm, but I won't actually able to do that. So the right way, you can kind of see that in order to measure the distance, I actually really need the machinery of the tangential plane in order to measure the distance. Okay, because by the time I'm actually measure the tangential distance, I need to go through multiple patch if it's very far away. Does that make sense? Okay, so this is actually like the example I talked about at the beginning. Let's say you want to fly from Istanbul to New Zealand, or sorry, New Zealand is a country. So let's say you want to go from Tokyo to San Francisco. You go up and down. Okay, how do you measure the distance? Okay, if you actually don't want to consider the entire curve, you can actually pick different amplitude and have a little bit of chart, and then in that chart you can actually define the distance. You would get approximations of that. You won't get because you actually only sample a few tangential plane, but not the tangential surface. But you can not continuously changing that in a tangent bundle. but you should be able to approximating that, right? You see what I mean? That's why you put a grid system on the Earth. And then of course you can see that if you put a grid system on the spherical, the problem is that in the North Pole and South Pole, that grid becomes zero, have zero size. Okay. I think machine learning driven manifold, you need a family of that. Okay, the UP map it there is actually to the boundary, and in order to anyway, so and then another important concept is actually related to what we talk about. A lot of time we are actually not creating model for one manifold, but we are actually consider the manifold that are evolving. Example is a U surface that have hardening or softening. Okay, so in this, or you can actually think about that. In this case, the mapping between one tangent space to another tangent space can simply be defined by the tangential map. Okay, the tangential map is actually different than the original mapping. That mapping the entire thing, that mapping a manifold. This mapping is actually the entire mapping from one mapping to another mapping. So this mapping, this local mapping, is actually the mapping only on the tangential space that are actually already linearized on the Euclidean space. Okay, so the very important thing that you should see here is that two mapping are related, okay, by these equations. Okay, so I basically map those points with this global mapping first from here to here, and I get this point, right? Okay, now I take the derivative of this mapping corresponding to the local parameterization parameter, then I can actually form that local mapping. Okay, you see what I mean? So this is actually, and then that mapping will be equivalent to I have a local coordinate system that are coming from F here, and then I create that local mapping. Okay, so, but in general, the local one and then the global one are actually two constraints. All of them are actually open to do that. One not necessarily identical, but you can actually getting that. Now we get to the more important part. I just want to compare. Now we go through the surface. So far, do you get some basic understanding on the surface on how to parameterizing it? So hopefully, I think the big message is there. Okay, so we consider smooth surface. There's a local coordinate system, and then in order to build that local coordinate system, you need a multiple mapping that are actually constructed. Now, I want to generalize this idea. So the idea of surface can be generalized. Okay, surface itself is a very specific concept for a subset of a Euclidean space of dimension 3, which is where the world we live in. Okay, we live in a, you can say, argue that we live in 4D space or whatever, in time as well. But spatially, we are doing in a 3D world, and then the surface of the 3D is what we regard as a surface. Okay, and that local parameterizations is actually one of the criteria. Now, if I actually want to generalize that concept into n dimensions, in n dimensions, we don't really see volume or thing, so we need to generalize that concept. A hypersurface is actually just the general size of the concept in 3D. Imagine that you have n plus 1 dimensions, okay, of a Euclidean space. Okay, that Euclidean space could be just some parameter. Okay, how many drugs I actually need to cure to actually control a cancer? That may be 10 different drugs, and then the amount of it will form a Euclidean space. Okay, you see what I mean? And what medicine combination of the medicine will be most effective will become a hypersurface. You see what I mean? Does that make sense? Can you guys imagine that? I have 10 different drugs, and then I want to find the optimum line where this thing works, and then I will form a hypersurface. Okay. If you do a classification problem, what I actually need is also forming a hypersurface, have multiple image of cat and dog. I actually want to create a hypersurface to actually distinguish it. Anything below that is actually cat, anything above it is dog, okay? Or you can use a vector machine to make it a flat line. That's another trick. But the hypersurface is actually just, you can think about it just one dimension less of the dimensions. Okay, so the surface and then the hypersurface are very similar idea, except that you are actually dealing with from R3 to Rn space, and then for the classical surface you deal with R3, for the hypersurface you deal with Rn plus 1, and then you are actually creating an open set for Rn instead of creating an open set that are actually for R2. Okay. So the basic idea is almost the same. You can also seeing that this thing is corresponding to this. They are linear independent of each other. Again, not orthogonal. Just need to be linear independent to each other. And then all of the previous things we talk about still apply. Okay, so that actually generalizing the concept. And then the surface is a very basic object that actually, hypersurface is a very basic object that we can consider as a model. So you can think about this. If for stress strain curve, you can think about stress strain curve as a functions that actually map stress to strain, right? However, you can also think about it as a surface or a manifold. Okay, you see what I mean? Does that make sense to you? Okay, so there are two equivalent ways to do the same thing. Okay, but if you actually think about it in manifold, of course you get the benefit of analyzing it as a manifold. You have curvature, you have all the stuff, geometrical tools, you can measure it, but you actually need to know what is a manifold. Okay, now the hypersurface itself, the surface itself is also a hypersurface. Okay, and the curve itself could be also a hypersurface. Do you understand what I mean? The hypersurface, hyper kind of in here mean a generalized concept that are coming from the physical intuitions now become a very abstract idea. Okay, so now a lot of the manifold are actually hypersurface, but not all the manifold are hypersurface. Okay, this is I need to talk a lot about set and then the Venn diagram. Okay, the entire universe, okay, as we know, is a manifold, but it doesn't come from some ambient space reduced by dimension 1. Okay, so not all the manifold actually need to be a hypersurface, but a lot of the manifold are actually just a hypersurface of a more general class that reduce 1 dimensions. Okay, basically because a lot of time you define a variable and then the thing that are admissible is just a subset of that variable. Like stress strain curve, okay, I define a lot of strain, a lot of stress, basically all the different combinations of stress and strain, but only a subset of them are actually good to describe metal or rock or actually a biological material. Okay, so you think about it, you can think about it like in a metaphor idea. Okay, so do you guys know the difference between the two? So they are identical in some sense if you do it perfectly. You can write the stress as a function of the strain as good as you consider stress strain as a manifold, but you just deal with different tools. And then different tools sometimes can give you surprisingly good results or accuracy, but the tools are actually different, okay? So like retention curve, you can also think about it as a manifold if you don't consider the difference between wetting and drying. Okay, permeability, porosity relationship, you can also consider it as a manifold. Okay, although you can argue that if I have a point cloud that look like this, and then I want to create a manifold, that is actually quite hard, right? If you do the porosity permeability calculation before, you know what I'm talking about. But that could also relate it to the sense of dimensions. Maybe we just miss some dimensions. This is actually what the kernel method did, is that I know that I'm probably missing some dimensions, so let me just cook up more dimensions in the feature space and then everything is linear. Then I just need a hyperplane to cut it. Also, yeah, one thing that I want to say is that there's a hyper surface and then of course they are also hyperplane, okay? And you're using it in kernel method a lot, the support vector machines, you use a hyperplane to cut stuff, okay? Things that are actually low dimensionally, in low dimension look very nonlinear, they look much linear in a very high dimensions. If you can find out those features that represent it. What we do with the benefit is that if you actually not include the boundary, you can always find some neighbor in the space. You see what I mean? Here, this is the opposite of the idea that what we talked about before. The previous idea is that I have some data, they could be lived in some high dimensional manifold. I actually want to using some trick to find it into a low dimensional manifold. But then the support vector machines for because they're mainly used for classification problem, the philosophy is kind of opposite. I actually have some highly nonlinear data. I add some dimension to make it linear. Now I can make a cut. Okay, maybe not that. Sorry, it's not making it more linear, but make it more separable, right? And then I can make a cut very easily. It could be just hyperplane. Okay. So okay, so I think we defined so far the hypersurface. Now we need to talk about what is a manifold. Okay. So I think that by now we know, and one important more neighborhood thing we want to talk about is actually the idea of neighborhood. So neighborhood, what do you guys think? What is a neighborhood? Who is your neighbor? I think your neighbor kind of form the neighborhood. But neighborhood, the idea of neighborhood is actually very important in defining the open set that related. So as you can see, what we actually, in order to construct a manifold, we simply need to do what we previously doing, but we need to cover the entire local parameterization to the entire manifold. Okay, does that make sense? Okay, for circle. So circle, you can consider it as a manifold. I simply need to have enough local parameterizations to cover the whole thing. Then I can actually say that we construct a manifold. Okay, so basically I parameterize it everywhere. So everywhere I have a parameterizations, and now I actually represent the whole manifold mathematically. That's all I say. Does that make sense? Okay. And here we are actually only considering the manifold that doesn't have a boundary. So there are also particular cases where the manifold have boundary, and that would be something that that could actually happen. Okay, so and here what we actually need to do is to extend the concept. We basically just need the local parameterizations to form a collections of the coordinate check. Basically, that coordinate check would actually, if I collect all the coordinate check and the corresponding topology there, I form something called NS. So this is actually the same as the original name that you actually see in C travel. You also have NS. So basically tell you in which coordinate system, which map I should use. So you can think that the coordinations check is actually like a local map, and then the NS basically tell you which collection. Let's see whether I have that. Okay, and in out of that collection, which of the checks you need to use, and then we need to make sure that the transitions is actually work. I think when I converted from explaining everything to here, I actually lost the symbol, but here I can actually, you can probably still see the special case. If I have a flat surface, then the mapping between all of these mapping are just identity. Does that make sense? Okay, I have a Euclidean space, okay, of R2, and I map it to R2. I just need identity so that I get R2. So that thing you can, so what I'm saying is that the Euclidean space is also a manifold, although you don't actually need to use there is no benefit of using the manifold tools to actually do any analysis, just treat it as a vector. This I actually already showing that. And then this is actually what the tangential space is. So everything that work in the hypersurface and surface, the idea also apply to to a manifold. Okay. The only thing that are actually different is that sometimes you would define something called arc-length functions just to tell you. If I actually run through that parameterization, how does this thing change? And you can integrating this along with that parameterization to give you the length. Okay, the same thing like if you want to compute the length of a circle, you would actually using the angle. Does that make sense? Okay, so and then one last thing that are actually very important for the Riemannian manifold, and I think the equation is a little bit displayed, is that it actually generate the reason that the Riemannian manifold is actually one of the most simplest, I would say, maybe somebody can disagree, most company use assumption that the material or the data is in is actually because it's actually in some sense very close. Locally they are just the Euclidean space, and then they have very nice property is that if I actually look at I can actually introduce a Riemannian matrix, and that Riemannian matrix is somehow related to norm that are in the tangential space. Okay, they're related. So with the Riemannian matrix are actually a second order that actually enable us to actually mapping to give us a sense of the distance, and then locally they are related simply to the inner product or the norm. Okay, so and this is actually the specific property. We also talk about that differential Basically, I just simply need both the mapping and then the inverse actually exists, and then we also need the derivative of it to have an inverse problem. So here I just want to end the lecture with some applications that I think is quite interesting, and they are some of them are from computer graphic. So this is actually a graph encoder with a folding base decoder. Okay, so what does the folding base is doing? Okay, so you start with that 2D grid, right? Okay, and then I can probably have multiple grid. Okay, not just one grid. And then I can use one application that this author did. I'm not involved in that research, but I just find it interesting, so I want to share. Is that they found a way to create a mapping that we just talked about. Okay, to build a correlationary chart so that I can flip it. I can actually folding it into an arbitrary shape. Okay, can be a car, can be a dog, can be a light. Okay, it could be an animal, it could be an elephant. Okay, but you can actually create. You can actually use the machine learning to actually in the decoder phase to actually create those 3D objects. Okay, because underlining the complexity, those 3D objects are actually manifold. And in that case, you can safely assuming that there's just Riemannian manifold. So what you actually need to do is that you don't learn this thing as a level set or whatever. You learn the mapping, okay? You see what I mean? I have two choices on representing the 3D thing. I can learn a level set function, right? Okay, do you guys all know what is level set? Basically, a scalar function to tell you, hey, if a equals to 1, I have a solid, a equals to 0, I have nothing. And then I can put this as a scalar function everywhere, like a level functions. But here I'm doing something differently. I directly want to learn the surface. So instead of it, I try to find out what the folding mean is to apply the deformation gradient on that flat surface to actually patching it. Does that make sense? And then if I actually find all the different way to flipping it, I can actually create the entire manifold. The folding net actually, Ming, our TA, actually wrote a paper on using it to, not using the folding net architecture, but using, directly using a supervised learning to create a U surface. Maybe I can show a little bit here. Another thing that are actually related and that are actually different is that if I learn the manifold, how do I reduce the dimensions? Okay, this is actually our own research group's work, and that is actually related to, but reducing the dimension, one simple way is to create a mapping that mapping from a curve, from a hypersurface back into a hyperplane. Do you understand what I'm saying? Because let's say I just have a curve, and then I have a different values on this curve, okay? I just store it in this curve. So at the very need, in the avian space, I need the XY positions to describe the positions, and I need some additional values that could be a vector, okay? Now, if I actually map it into a straight line, I can actually only have the X coordinate, and I can actually reduce one dimensions. But the thing is that in a high dimensions, you don't actually need to just get a hyperplane. You can actually reduce even more dimensions geometrically by actually flattening it, by adding even more constraint. Okay, you see what I mean? So you're adding the constraint. You understand what I'm saying? It's like the Fowler element each time. What happens if you put a Lagrange multiplier? Okay, if you statically condensing it, you would find out that you actually can take out 1 degree of freedom, right? Okay, so this is actually one way to doing it. If you add enough and you find a specific way to fatten the nonlinear data, eventually you get a new parameterizations where you contain the same informations, but then the whole data is lined on a flat line so that all the linear tools actually work. Then that would be very simple. If I don't have to deal with the nonlinear data. Okay, sorry. I still need to deal with the nonlinear data, but I deal with the nonlinearity by dealing with that mapping, and then the search is conducted in a flat surface, which is of course very easy. Okay, so how do you conduct a search from a flat surface? You just measure the Euclidean norm, right? And then you don't need a global norm, and you don't need to go through the fiber bundle to say, hey, by the way, I need to measure the distance. Tell me under that 1,000 different local parameterization, what is the difference? Okay, so that I think that I sort of running out of time. Maybe next time I can show more details. I think basically the 3 different way to doing it.